So whatever it shows on this screen will not be what we liked last time. This delayed stuff, it is not recorded.
Oh, so it's picking your video up quicker?
It shows, right now it projects what I do have on my laptop, but it records from the larger camera here. So if you focus larger camera on the screen, then maybe we can get some fun stuff recorded. Hi Jim, how are you? Do you guys know what is interaction picture? Generally, does it ring any bells?
I've read about it the last couple of days.
Interaction picture. No?
Interaction pictures.
No, it is not like Columbia pictures or interaction pictures. It is a term in quantum theory. No? Like Schrödinger representation, Heisenberg representation, interaction representation. Yes? Or not quite? So there is a... Huh?
Feynman diagram or something.
It is like before one goes to Feynman diagrams, one needs to take like to become comfortable with these simple ideas. So in perturbation theory, we do have unperturbed Hamiltonian and the small perturbation, but all equations become wrong and adverse because of the trivial evolution, because of H0. So it would be great if you could avoid it, to write the same equations but without H0. So basically interaction picture, interaction representation is the way to avoid it. Yes?
What I remember is basically just a way to separate the time dependence between the wave function and the Hamiltonian.
Mm-hmm.
Hello.
Very good, thank you. How are you? Okay, I think we are majority. 4 out of 6, or if counting me, 5 out of 7.
And I don't think Sam can come because of his dog meat. So that would be
Huh?
4 or 5.
That was dog meat?
Dog meat. He has obedience training. That's 6.
Who's being trained?
Dog.
Okay.
Why would he be?
Maybe he's not very obedient to the dog. Makes sense, right?
Not at all.
So, what are you guys doing next week?
That's spring break.
So you're traveling home for relaxation?
No, I'm going home Friday after my presentation and come back like Monday. So that'll be good Tuesday. Sorry, Tuesday.
Okay. Do you want me to help you to have more fun during this week?
No, probably not. Because I know I have a lot of work to do.
Okay.
So
So
I know Javed's going to APS. Do you know if Dayan is going to APS?
yes,
So that's.
he will make his practice talk on Friday
Oh yeah.
on the group meeting.
Is that channel not working?
Camera does work.
No, that not your.
This camera works very well.
Oh.
What you see on the big screen is a projection of my little camera, but what is being recorded is what is on this camera.
Oh,
So when I will start doing something useful, I will turn it around. So you serve as a proof that it is an actual class, not me just standing in front of camera and writing equations. So if you have really nothing to do and want to entertain yourself, you can practice a little exercise. So it's very, very optional. I will not ask if you did or did not. You can just, if you do it, you can just approach me and request more credit. But We are here for fun, not for credits. At least myself. So, right now we did solve evolution of two-level system with time evolution method precisely, and by approximately by first-order perturbation theory, right? If you want to try a connection to more practical systems, you can use the same code and expand number of states from 2 to like 100 and see transition probability from ground state to either one of those. If they all have the same transition dipoles, but are a bit offset in energy. And then it will be like simplest example of computational spectroscopy, right? You'll make an artificial system, maybe equally spaced, and then you will find probability that monochromatic light excites some of those, and with which rate the ground state will be depleted. It would be great fun to do it here, but the semester will end soon. Even if we all volunteer in some extra time, still it is too much to do in class. But we will finish the perturbation theory tomorrow with your outstanding presentations. which you will happily submit before midnight today. Some of you did submit already. What are we going to do next? What is our plan? So I have a clear idea. Just try to wrap it up from the right angle. Perturbative solution is good only for very short time, initially. But what if the pulse is strong? What if the system is perturbed by some strong interaction? What if we are interested in more than depletion of population and we need some more complicated observables? For example, if we apply the same quantum model to spin, we may need polarization not in Z but in X and Y directions. What if we go from the occupations and probabilities to phase-sensitive experiments, where phase of wave function does matter? I'm not offering to measure it directly, but where it does matter, like wave mixing, wave interferometry, and some photon echo, advanced spectroscopical techniques. So there, in such a process, one needs to keep track of the phase, and one can go a little further away from big perturbation region, on one hand. On another hand, generally, we may think not in the narrow window of optical spectroscopy, but any interacting quantum system. How does energy excitation flows from one system to another? So we are going to look more onto quantum dynamics of excited states. And before we start it, I suggest we make some preliminary steps here in the lab. So you do remember, or if you concentrate, you can find the right page in the book or in your notes, the explicit expression for perturbative solution. Okay? So it does include Hamiltonian of interaction, but when you derive it, and if you do different orders, anything we do, we have an obstacle that stops us from being very quick. There is an unperturbed Hamiltonian that contributes very trivial thing, just boring phase accumulation, but we need to keep it as an operator everywhere. Is there a way to get rid of unperturbed Hamiltonian and make equations simpler? since main contribution comes from the interaction Hamiltonian, can we design such form of quantum equations which contain only interaction Hamiltonian? What is the answer?
Yes.
What did he tell?
Interaction picture.
Did you hear it before?
I knew that it was yes by the way that you asked the question.
So you know Schrödinger representation or Schrödinger picture, Heisenberg representation, right? This includes something.
You mentioned it once in class.
And I mentioned it another time in another class. Okay. So interaction picture is change of system of coordinates in Hilbert space in such way that unperturbed Hamiltonian disappears from as much as possible. So the goal is to eliminate it. And if we will do the same things as we did before for our poor 2L systems in this interaction representation, we should get the same result. So we are going to do something that will bring us to the same solution as we got before. But we may want to check to prove to ourselves that it is valid, and we may get practice how to convert all equations and all coding into this interaction representation, because without this preliminary step, we will not be able to go to the next chapter. So we are basically investing effort into what we are going to do in the near future. Yes. Show me, please. I don't know if it is. Oh, remember last time it didn't record the interesting artifact of the delay, but now maybe it will be recorded and we will.
No, but the screen is not set up correctly.
It is. You can come up and then we will make a trim. Yep. We will make a clip of. No? You don't know?
I'm ready to go. No.
Go.
Just look there and try to wave hand, imitating the.
No, like,
What?
Yeah, the oscillations.
He's not having his time
No,
display.
it's in the computer.
just look on his computer.
Try to.
Yeah, but he's showing only 2 images.
But if you try to wave it quick,
No, the
see?
thing-
Because it's not multiplying, they are showing only.
Last time we had like 10 images right away.
I mean, he's just overlapping one each other.
So.
So tilt the camera more towards you.
Tilt the camera to the laptop,
No,
and then
towards the screen. Just pan. No, that way. Oh,
And so you get that straight in the laptop.
this should be in the laptop.
Yeah. Oh, the other way.
No, I
Can you
guess this.
No.
Then
Towards the
till
you
it
get more screen.
More
Yeah.
this
screen. Yeah, turn the.
turn to the.
Yeah,
There you go.
Okay, that's too
Oh,
much.
okay.
Now flip it up a little bit.
Now that's too.
Now wave your hand a little bit.
Oh yeah.
And now try to make it quicker.
No, it's feel. They go like this.
Still is going.
Well, I think you got some fun. So basically I don't need myself, I need just the board. But I will be as an aberration to this. So here are my limits for writing. So if you just have nothing else to do, you can do what we did before for 100 levels. It is very easy programming, but then it will be realistic. If I get a chance to teach this course again, maybe it will be a formal task, but now, no time.
And then you also have it.
So the goal is in the direction picture. We move H0 if possible. So we will redo everything we did before in a little bit different way. So there is a Schroedinger picture, Heisenberg picture. Schroedinger picture when wave functions accumulate phase and most operators are time independent, except crazy perturbation. Heisenberg picture when we move accumulation of phase from wave function to operators. And interaction picture is applicable only when we have combined quantum systems, system A and system B. And it is like Heisenberg, the accumulation of phase is on operator rather than on the wave function, but it is critically important that there are two systems and each of them has its own phase accumulation. Right now, we can pose this goal, but we cannot do it because we have only one quantum system. What we have done before and what we are going to do for a long time, maybe until the end of the course, is semi-classical approach. Semi-classical because our perturbation, our light, is classical. It is only a driving force that we cannot change. We do not have feedback from our quantum system back to the light. Although in the nature, if quantum disappears from quantum system, then some mode of the electromagnetic field get increment, like in lasers. The active center emit quantum, and then this quantum resides, energy resides in the mode of the resonator field. But now, the perturbation is something that we cannot change. It doesn't depend on our equations. So in some sense, it is classical. But major part of our, but we have half, the system that we explicitly model is quantum. It is not classical, half classical, semi-classical approach. Therefore, we do not have an opportunity to explicitly play interaction picture, but we can do rotating frame. So it doesn't mean that we have a window frame that is going to rotate and fly around the class. Frame, it means like system of coordinates. Okay, that's it, in principle. The rest are technical details. Suppose we have wave function in the rotating frame that get all the accumulation of the phase due to evolution operator that was developed due to unperturbed Hamiltonian. But basically, there is no integral to the time-independent Hamiltonian times time period. And let's tell that it is our actual Schrödinger wave function that depends on time, and it accumulates everything as it goes. So we want to use trivial evolution, trivial phase accumulation, as we want to get rid of it, and we want to do some tricks. Any objections to this equation? Standard, right? Solution of Schrödinger equation. So if we do not have perturbing Hamiltonian, perturbation, then it will be just solution of Schrödinger equation, where this would be initial, this would be final state, right? Now, if this is correct, we can multiply it by conjugate evolution operator from left. Because it is Hermitian, this conjugate times non-conjugate will erase each other, and then we have the definition, so that wave function in the rotating frame is the inverse evolution applied to our regular wave function in Schrödinger picture. Okay? Nothing heretical. The goal of quantum mechanics is to predict observables. So if we have Schrödinger wave function, Schrödinger picture operator, and Schrödinger Bryan-Cat. Then this is our implementation of the main goal of the quantum theory. Can we replace this Bryan-Cat according to this definition of the rotating frame? So we will plug in this definition. Why are we going? If we are changing system of coordinates, both wave function and operators change. So the question is how operators will change in the new frame. So I can write under here. So this cat will be replaced by mu0 psi in rotating frame. This bra will be replaced by psi rotating multiplied by u0 with dagger for conjugation. And here it is still Schrödinger operator, right? No lies. Always correct up to now. Now, we already have rotating frame bra and rotating frame cat on left and right. Let's call this it will be new operator. Or we can use the same label like operator A in rotating frame. Yeah. I don't know, maybe it's not a common notation, but
I'm just like
Right.
using this.
yeah. Good. So if we accept these definitions, let's make the following experiment, following intellectual experiment. What if we do have our unperturbed Hamiltonian and we do have our perturbation, which is time dependent? Before we were trying to solve Schrödinger equation for this perturbed Hamiltonian. So how would Schrödinger equation will look like in the rotating frame, first, in general, and second, how would Schrödinger equation look like in the rotating frame in presence of the perturbation? So we are going to apply this prescription. So rho general operator in rotating frame is evolution operator before and after when this operator is expressed in Schrödinger form. So we are going to use unperturbed and perturbed Hamiltonians in place of A, and then we are going to check whether the Schrödinger equation will remain in the same form as we agreed to see it if we do this change of coordinate, this transformation. Okay? I'm going to erase it and keep going along the plan. And I will also erase this option. If you wanted to, you already had a chance to. Interaction picture, remove H0 if possible. Yes. Rotating frame. Yes. The rest can be probably removed. Example. Examples are easier to think about. It is very meritorious for scientists and mathematicians to make abstract thinking, but for human beings it is a little easier to look on examples and then try to go to more abstract. So what if we do have H0 is energy state 1, energy state 2, 0. Evolution operator is E minus I h bar E1t, E minus I h bar E2t, 0, 0. This all is in Schrödinger picture. And the perturbation of Hamiltonian is 0, 0, V times cosine omega t, V times cosine omega t on the off time. So how will these operators change if you go this and these operators change if you go into this rotating frame? Again, why are we doing it? Because we want to avoid zero unperturbed Hamiltonian from any equations. And we hope that we will get Schrödinger equation that doesn't have this operator. So Schrodinger equation without Hamiltonian, hopefully. So I am going to practice. I'll do it myself. I thought that I can invite some of you to help, but it's too simple. I can do it myself. If it would be a hard task, I would ask you. So our prescription is multiply by evolution operator, direct and inverse from front and from left and to the right, each of the operators. So if we need H0 in rotating frame, will be U dagger H0 U0, right? Which will be left space. Yes. So if it is inverse evolution, it is the same as direct evolution, just with different sign. I H bar E1 T 0 0 E plus I H bar E2 T. Here we have E1 E2 0 0. And here we have operator for direct evolution. E minus I H bar E1 T E minus I H bar E2 T. I just don't want to write something that you will not see in the screen. Okay, row by column, row by column. So it will be this evolution plus I H bar E1 T times E1. So I'm multiplying first two matrices first, and then third matrix second. Row by column. 0, row by column. 0. Right? So for this element, this row by this column. 0. Yes? For last element, E plus I H bar E2 T1 times E2. Multiply. Let's play lazy and just write U0 because we can see it here. And then multiply row by column, practice row by column, this row by this column to get the final matrix. Can I do it?
Yeah.
Says, okay. So this row by this column will be E plus I H bar E1 minus E1 times T times E1. That's it, right? Agree? Row by column. 0. 0. Here will be E minus I over H bar E2 minus E2 T times E2. Right? So it will be E1, E2, same as we started from. So this transformation from Schrodinger to rotating frame didn't affect the unperturbed Hamiltonian. Do you think it is a favor? It's just operator. Let's
Did you say favor?
failure. Failure. No, it is not failure. But I'm just trying to sit on your plate and say, he is telling that we are going to get rid of unperturbed Hamiltonian, but unperturbed Hamiltonian survives, and it is here again. Right?
Isn't that your not Hamiltonian?
No, it will not disappear. But when we will plug in everything into Schrodinger equation, something will become simple. Promise. Or at least, what to say, in a reserved academic form. There are serious reasons to expect positive results. So, you can summarize it here. H0 in Schrodinger and H0 in rotating is the same. And then we can erase this stuff. Next step, not like next person to the board. We are taking the Hamiltonian perturbation from Hamiltonian and try to cast it in the rotating frame. So H prime in rotating frame, U0 dagger, H prime Schrodinger, U0 without dagger. I should have erased it. I could change just operator in the middle and keep left and right.
But won't it just be the same? Because
Yes.
The zero.
Yes. Well, maybe you can multiply matrices directly in the brain without writing, but in average it is much easier to.
No, but everything kills.
No, not everything. Let's do it explicitly. Let me practice it once again. Plus, plus, zero, v cosine omega t, v cosine omega t, 0. And here we do evolution in the right way. Minus I, h bar, t, 0, 0, e minus I, h bar, e t. So let's practice row by column. And we do first two matrices first and third matrix second. Row by column, here we'll have 0. Now, this row by this column, we get intensity of perturbation, cosine omega t times e plus I h bar e1t. Here we will get v cosine omega t times e plus I e2 or h bar t. And here 0, right? And then we multiply it by u0 and practice row by column once again. So this row by this column, 0. Now this row by this column will be v cosine omega t e to the power plus I h bar t. What do we have as an argument? So here exponential was accumulating phase with sign plus, and here it accumulates phase with sign minus. Here it is energy of state 1, here is energy of state 2. So it will be E1 minus E2. Okay? And here it will be the same V cosine omega t times minus I t h bar, and here E2 minus E1. So difference in energies, but since off-diagonal elements of Hamiltonian are typically conjugated, it is different sign. 0 here. We are yet far from our goal, but does it look promising? Do you feel happy? Or you do not understand how this ugly expression can make anyone happy?
Is it stable with time?
Good. You either know the answer or you have a gift to predict.
No.
Or maybe you toss random words and they accumulate into right.
I did that last semester. I mean, last spring quite well.
Yeah, yeah.
But I do know that the time evolution operator, is stable depending on how you apply it.
So we are going to drop some terms and pay nothing for it.
Oh, that's nice.
And then to justify it, we will call it approximation. Right? How things work. So we do have interaction from the perturbation Hamiltonian in the rotating frame, and we can remember that.
Is that in frame?
Huh?
Is it in frame?
Yeah, rotating. Rotating.
No. Is it in the picture frame? Can it be seen?
Yes.
Okay.
Let me make it that you can see. Better? So, cosine is E plus I omega t minus I omega capital T divided by 2, right? Good. So, with this knowledge, our interaction Hamiltonian 0 V times V divided by 2 exponential plus I omega capital T times E plus I T h bar E1 minus E2 plus, is it seen well enough? This is most interesting, well, not second of importance of our today's meeting. Plus E minus I omega t times same term. E plus I t h bar E1 minus E2. And close the bracket here and there for the whole matrix. This one will be 0, and this one will be same as here, but conjugated. So what is bigger, E2 or E1? Well, you can plug in any numbers. You can even make them equal, but typically we order them in ascending. Typically 2 is bigger than 1. Okay, this one is negative, and this frequency is negative. Right? You see it. So it is minus omega capital, and here this subtraction also negative. So it is exponential into the power of 2 negative numbers, and it is imaginary. So it is accumulates phase twice as quicker. Something quickly oscillating. Quick oscillation. Here, E1 minus E2 is negative. E1 minus E2, negative. omega capital is positive. We always keep in head resonance conditions, that this difference in energies and frequency of light are approximately equal. So this will be very slow oscillation. So do you know how to deal with quick oscillations? Maybe you do, but it is not fun. Let's drop it and tell that it is like rotating frame approximation. We just drop quickly oscillating terms. As a justification of this approximation, we are going to program whatever we do, program the time evolution of this two-level system in this frame and see if you get the same result or different result. Right? If you get the same result, then this approach will be justified. Well, not in mathematical sense, but in rational sense. And this term will be the same as here, but with flipping the signs. E over 2 E minus I omega t times E minus I t h bar E1 minus E t. And then the second part I already dropped because we agreed. Right? Some people call, since phase in the terms, listen, in quickly oscillating, phase accumulates in the same direction if you consider rotation in complex plane. Phase coming from the system itself rotates one direction, and phase accumulated because of perturbation rotates in the same direction. So they are co-rotating. The other term is when they accumulate phase in opposite directions. So they counter-rotating. So we keep counter-rotating terms and drop co-rotating terms. Good? Even if you do not believe it, probably the line of narration is good enough to follow. Okay, so I'm going to record our intermediate result on the top of the board, and then our next step is to rewrite Schrödinger equation with account of everything we did by now. So each camera go up. Not as much, or H prime rotating, 0 on the diagonals. We can put V divided by 2 up front, and here will be exponential I H bar T of E2 minus E1 7 omega capital plus sign, right? So two positive numbers are coming with opposite sides. I have just rewritten what was there, the term that we kept. And here we do have exponential IT bar. E2 minus E1 minus omega cos theta. Okay. We do have all components. Now, what is our plan? How are we going to rederive Schrodinger, well, not rederive, recast Schrodinger equation in rotating frame? We are going to write down Schrodinger equation in regular, in Schrodinger frame, and then plug in the definitions wherever it is possible. And just then call mathematician inside ourselves and see what happens. Erasing as much as possible. Any objections?
What's that second term? K8.
So, yeah, good objection. So zeros, unperturbed Hamiltonian and perturbed Hamiltonian, both in Schrodinger point of view. We can replace these two cats onto our definition of wave function in rotating frame. Evolution acting on the cat in rotating frame. Here we have the same d dt sub 0 psi true. Right? No corruption yet. No cheating. What do we do next? We are applying time differentiation to the product of evolution operator and wave function. So we get d d0 dt times psi in rotating frame plus evolution times d dt of the wave function in rotating frame. And the rest is unchanged. What do we get if we take time derivative of the evolution operator?
Evolution operator times the exponent. Take the derivative of that.
Let's we all need to pretend that we like abstract thinking, but let's do a practical example. Let's do dt of e minus I h bar e1t 0 e minus I h bar e2t. So just derivative of each term. So it will be minus I h bar e1 times e 0 0 minus I h bar e2 exponential minus I h bar e2t. Would we get this answer if we do E1, E2, 0, 0, E minus I h bar E1t, E minus I h bar E2t? Would you agree that multiplying these two matrices will get this answer? If we multiply matrices that are diagonal, then it is just multiplying each element. So we can write it down as minus I over h bar, unperturbed Hamiltonian, times evolution operator. Right? So evolution operator basically follows same equation as wave function. Time evolution of the evolution, time derivative of the evolution is Hamiltonian times evolution operator. So let's use it in there and erase this exercise. Schroedinger, evolution operator, evolution, rotating, and then frame each part. Which step would you do at this point? Right now, many terms do have evolution operators, but evolution operators everywhere are in the first power. But if you are going to convert like Hamiltonians into rotating frame, we need two evolution operators, direct and inverse. So nothing, yes, from the left. So multiply each term by u dagger from the left and just as a mathematical experiment and see what happens. So minus I h bar u dagger h0 Schroedinger u0 times psi in rotating plus u0 dagger 0 ddt psi in rotating equals minus I over h bar. Better keep different line, otherwise it will be minus I over h bar. And here we multiply this term by inverse evolution from the left. So it will be u dagger 0 h Schroedinger 0 plus u 0 dagger h prime perturbation times psi in rotating frame. Good? Can we observe some simplifications? Do we have any equal terms on the left and right? Which one?
First one,
So this one?
and then that.
So we can cancel them, right? Note that your unperturbed Hamiltonian was there. You just suggested me to remove unperturbed Hamiltonian from both left and right, and now we do not have it anymore. Now what we have left? This u dagger times u, since it is a Hermitian, they cancel each other, so I converse. And here it is the definition of the perturbation in the rotating frame. So it will be h prime in rotating. So we are getting dt psi in rotating frame minus I over h bar h prime in rotating frame times psi in rotating frame. So if we did this trick, if we rotated our system of coordinates for wave functions and operators in this rotating frame, then Schrödinger equation does not contain this trivial operator of evolution. So we can use this operator, and then if we need, we can either find the answer in the rotating frame and analyze it, or if we are so eager, so curious to get the answer in the Schrödinger picture, then we can rotate it back after we find the solution. Okay, so what we are going to do is make a copy of the code, and there we can go off record of this image very soon, but we still be able to record the MATLAB programming. We are going to replace our cosine omega t to these exponentials. And if the resonance is exact, then it will be just 1 and 1 here. So in this rotating frame, under condition of exact resonance, Hamiltonian becomes time independent. This is a great achievement if you are dealing with multi-levels. With two-level system, you can solve by any method. But in bigger systems, any little bit of simplification is appreciated. If you do not have exact resonance condition, since we are close to it, those exponentials will be changing very, very slowly. So we can, if we do traditional integration, we can integrate with reasonably big time step and get no error. So it is very comfortable numerical arrangement. What I'm going to do, bring up to the screen the MATLAB code, make a copy of the code, and replace the interaction with Hamiltonian to the stuff, and then try to solve it exactly and by perturbation theory and see if we get same or different results.
Is this the, are we doing the scanning one or the original?
Original. Scanning too much. I haven't designed how to formulate a homework, but let's just make it as fun and then maybe we'll design something. Objections? Questions? No? Okay. So I will be just sitting and programming, and then we will exchange ideas and questions as needed.
She has such a pleasant voice.
Maybe it was a casting. Most pleasant voice for important application. It doesn't show what I have.